Welcome to the Da Vinci Academy Histology video course. The entire video course is available on YouTube and covers all of the fundamental principles of histology and relevant cell biology. You can find all of the videos from the course by clicking the Histology playlist link in the description below, and then you can access the corresponding practice questions and histology lab videos by going to our website, which is also linked in the description below.
Hi, I'm Dr. Lee, and welcome to Histology. This is the first of the series of histology lectures titled The Principles of Histology. Today we'll talk about what histology is and why we care about studying it, followed by discussing the two very important tools in helping us study histology. And these are the histotechnology and microscopy. Let's begin. Histology is the study of tissues. And what are tissues made up of? It's surprisingly simple. They're made up of cells and extracellular matrix, or ECM. That's it. So why should we care about tissues? Well, we're made of it. And to learn histology is to learn how we are made up and how we function. And I gotta tell you that injuries and pathologies that we suffer, they occur at the atomic and molecular levels that manifest at the cell and tissue levels. And as much as we'd like to study these injuries and pathologies at the atomic and molecular levels, at least at present, cell and tissue levels remain to be the most easily and economically accessible forms of ourselves for diagnostic and for treatment purposes. So it's pretty important. So let's talk about, in general terms, what tissues are made up of. As mentioned earlier, cells are the first ingredients. And in terms of the cells, we have countless variety of types of cells that make up our body. We have cells that are cuboidal. We have these discoid or biconcave cells without nuclei. We have cells that have fused their cytoplasm, so they're multinucleated and have intracellular mechanisms that allow them to contract and relax. And we also have cells that are really long, that have long cytoplasmic extensions that extend from the spinal cord all the way down to the muscles of our toes. So a wide variety of cell types make up our body and our tissues. And as you can see, there's a lot of spaces in between the cells in this image. That's not really an empty space. That's where the ECM, or extracellular matrix, comes in. In terms of the ECM, there are three major categories of structures that comprise it. First are the fibers, second, the ground substances, and third, the fluids. In terms of fibers, there are three main types of fibers that are found in most tissue types. First are the collagen fibers. These are these long, fairly thick, and very strong type of extracellular fibers. They're really good at resisting pulling forces, so they provide strength to the tissue. Then we have elastic fibers, these squiggly gray structures. And as the name suggests, elastic fibers are, well, elastic. They can stretch and recoil back to their original shape and length. And we have reticular fibers, these green structures. And as the diagram suggests, they're short, they're thin, very delicate, but they're also really good at forming these fishnet-like networks the cells can grab onto and hold onto. So they're really good at providing some architectural structures. So these are the three main types of fibers found in the ECM. Even after displaying these fibers, you will note that there are a lot of empty spaces still left behind between the cells and the fibers. These are not empty still, they're filled with the ground substance. The ground substance, there are three different types again. There are glycosaminoglycans or GAGs, glycoproteins, and proteoglycans. These are macromolecules indicated by these yellow squiggly structures. And these structures are really good at anchoring the cells and fibers in place. And these structures, the ground substances, are usually carbohydrate-rich macromolecules, which means they're also good at holding onto or attracting water into the extracellular space. So here comes the third ingredient of the ECM, which are the fluids. The fluids are essentially very similar to plasma in the blood. They're mostly water, and they're sometimes also called interstitial fluid. So tissues are wet, and the fluids play an important role in allowing macromolecules, gases, and ions to be dissolved in it in order to bathe the cells and to nourish them as well. Here's the real micrograph of a tissue, and all of these ingredients are portrayed in this image. Upon closer inspection, I hope you're starting to see some patterns. A lot of these oval and dark staining structures are all nuclei that belong to the cells. So based on the shapes of the nuclei, you can already tell that there are a number of different types of cells that's populating this tissue. In terms of the ECM, in between these cells, we have fibers. And of the fibers, we can see two types. These pink and thick and bundly or ropey type of fibers are the collagen fibers. You can see many of them now that I pointed some out. The second type of fibers we can see are these hair-like structures that are sometimes branchy. These are the elastic fibers, providing elasticity to the tissue. And the third type of fibers, the reticular fibers, you'll just kind of have to trust me. They're here in this field, but unfortunately, reticular fibers are so thin and fine, sometimes they don't stain well with typical stain, so we have to apply special staining techniques in order to see them. So for now, trust me, reticular fibers are here. Now, in between the fibers and cells, we have these pale staining or non-staining regions, and these areas are where the ground substance would be present. And where the ground substances are, they're fluids. So this is well-hydrated tissue that we're seeing in this field. So let me ask you the following question. If all tissues are essentially made of the same ingredients, cells and all of those ECM components, why do various tissues in our body look and function so differently? Like these. So these are all tissues taken from a body, and they look very different. The reason for that is because of the types of cells that are the main components of that particular tissue. So for example, while we have variety of types of cells in this one, over here, and even in this tissue, the majority of the functional cells in these type of tissues are limited in terms of the variety. Furthermore, the proportion of the ECM components that make up the tissue can also influence how they look and function so differently. So for example, on this one, this tissue is comprised mostly of this pink bundly ropes, the collagen fibers. So collagen fibers are the major ingredients of the ECM in this tissue. And in terms of the ground substance and fluids, there are very few pale staining regions indicating the ground substance and fluids. So this is a collagen fiber rich and ground substance poor, although they're there, type of tissue that functions very differently from a tissue like this or even these. Now, it's important to remember that a number of these different types of tissues will come together and function as a unit and become an organ. Here's an example of an organ. This is a developing tooth and the supporting structures. And although we don't know all the tissues of the body yet, we can still see from the staining patterns that there's perhaps 1, 2, 3, 4, 5, 6, at least 6 different types of tissues that's comprising the developing tooth and the supporting structures. Now the number of organs will come together and give rise to the next level of body organization, which is the organ systems. things like the digestive system and the muscular system, then all the organ systems will once again come together and give rise to our anatomy, our body, which means to study the histology is really to study our anatomy at the cell and tissue level in depth, both figuratively and literally. Now, you may have noticed, though, that studying the tissues isn't something that we can so readily and easily do, especially with our naked eyes, which means we need a number of these technical steps, collectively called histotechnology, in order to get the tissues ready for microscopic observation. Then we need the microscopes to actually look at them. But before all of that, first we need tissue acquisition. Get the tissues out of the body. There's a number of different ways to do so. The least invasive way is cytological swabs. We're taking a swab and rubbing it against the part of the body where there are readily shedding cells like the oral cavity, pap smear, the cervix, that type of things. And of course, we're not actually looking at the tissues. Rather, we're looking at the cells. But it's a really quick way to identify any dysplastic cells. Then we have biopsies. This is a little more invasive, where we're taking a small piece of the tissue out of the body, either from needle biopsy, punch biopsy, or even incisional biopsy. But the tissues that we take out tend to be smaller. Then we have the surgical resections. This is, of course, the most invasive form of tissue acquisition. We're actually going into the body and taking a small segment of an organ. So let's say that we're taking a small region of the small intestine. Once a piece of tissue or an organ has been taken out of the body, the problem now is that the cells and the tissues will quickly start to degrade. So the next step in histotechnology is fixation, which is designed to stop this degradative process by applying either heat or other forms of chemicals that'll denature a lot of proteins. One of the most common fixatives nowadays is the chemical formaldehyde. It penetrates the tissues at a rate of approximately 1 millimeter per hour, which means when we have a big piece of organ like this, it's probably a good idea to cut it open so that the internal structure is exposed to the formaldehyde too, so that the fixation occurs faster. The process of fixation changes the color and texture of the organ, so it tends to harden the tissue and changes the color from bright red to, say, various shades of gray and brown. Once the organ has been completely fixed, the next step is actually to take even smaller section out of that organ. And that's because we can't put this large organ under the microscope and see the tissue and cellular details. The next step in histotechnology is the tissue processing. Nowadays, we have an automated tissue processor such as this, where the tissue is placed and is treated with a number of different chemicals and washing agents, essentially to replace all the fat and water content of that tissue with some kind of a hardening agent like paraffin. And this is done to harden the tissue even further than the fixation alone. And this makes really thin section of the tissue possible. The next step is embedding. We take the hardened tissue now and place it in a mold such as this, and we flood this mold with liquid paraffin, which then hardens along with the tissue so that we end up with a hardened paraffin block, which looks like this. And when it comes to embedding, it's very important to do so in a thoughtful way and almost think ahead as to how the tissue is going to cut so that each tissue slide would reveal the most information about the tissue as opposed to perhaps a tissue that may be cut this way if they're embedded the wrong way. The next step then is sectioning. We mount the paraffin block on a microtome, which kind of looks like this. It has a mounting area here, a sharp blade down here, and a hand crank. And tome refers to cutting. And micro, you know what that means, small. So it's a small cutting tool. And with each crank of this wheel, it advances the paraffin block just slightly forward and brings it down against the blade, thereby allowing us to make a really thin tissue slide, like so, that varies between 4 to about 10 microns in thickness. When we have a good number of serial tissue sections, then we take that ribbon of paraffin slices and place it on a warm water bath like this. And it allows the paraffin to float on top and smooth out any wrinkles that may have been introduced during cutting. Then we take a glass slide like this and dip it under the water and gently lift one of these tissue sections up off the water. And now we have a glass slide with a single tissue section. The question now is whether we're ready to observe this tissue under the microscope. And the answer is no. That has to do with the fact that now the tissue is so thin, it's become transparent. And plus, there's all these paraffin that's in the nearby area. That's where the next step in histotechnology comes in handy, which is the staining process. First, we remove the paraffin by applying some heat. Then we apply a number of different dyes and washing agents to remove some excess dyes. And of course, nowadays we have automated staining machines like this. Then we place a glass cover slip on top of the stained tissue to protect it. And finally, we're ready to observe the tissue under the microscope. And to get here, we had to take a number of different steps, starting all the way from the surgical resection, fixation, taking even smaller section out of the organ, then processing, embedding, sectioning, then staining to get to a histological image that we can observe under the microscope. Now, before we start talking about the different types of microscopy, let's spend a few minutes discussing the different types of dyes and other staining agents used to bring out the different features of the cells and the tissues. First, we have H&E, which is the most common combination of dyes, where H stands for hematoxylin. This is a chemical that is positively charged, which means they're basic in pH. So hematoxylin dyes the things that are negatively charged or acidic in nature, something like the DNA or RNA, where A stands for acid, which are rich in nucleus and ribosomes, will stain well with the hematoxylin. This dye has blue to purple hue, so in this image, identify the things that are purple to blue. And hopefully your eyes are going to these circular structures. These are all nuclei, and these punctate darker purples in the center, these are the nucleoli where the ribosomes are assembled. So nuclei, nucleoli, these things that stain well with hematoxylin are said to be basophilic in nature because they're attracting the hematoxylin, which is basic in pH. The E in H&E stands for eosin. This is a negatively charged dye, which means they're acidic in pH. So they are attracted to the positively charged or basic structures in the cells, and many proteins in the cytoplasm, being basic in nature, they will stain well with eosin, which has pink to red hue. So we're actually seeing the lovely pink cytoplasm staining well with eosin. And of course, structures that are staining well with eosin are then said to be eosinophilic or acidophilic for attracting this acidic dye that is the eosin. Another staining technique is histochemistry. And as the name suggests, we're essentially using the natural chemical interactions between the tissues and the chemicals. And when you think about it, H&E is actually a type of histochemistry for using the acidic and basic natures of the dyes and the tissues. But there are other histochemical stains out there also that are commonly used. One is trichrome. Tri stands for 3 and chrome stands for color. So this is a combination of 3 colored dyes that are most commonly used to visualize collagen deposits. So things like the keloids or chronic hepatic cirrhosis type of tissues will be stained with trichrome to see how much collagen fibers are being deposited, which shows up as this beautiful blue colored structures. Another histochemical stain is the periodic acid Schiff. This is a chemical that reacts with carbohydrates in a tissue or cell and turns them into this beautiful, intense red or magenta color. So as you can imagine, we would use periodic acid Schiff to visualize where carbohydrate-rich areas are within a cell or tissues. Next, we have immunohistochemistry. And as the name immuno suggests, we're using some specific interactions between the antigen and antibody to look at the expression of specific protein of interest. So in order to do so, first we apply the primary antibody that's designed to go and bind to the protein that we're interested in looking at. And this protein could be the membrane-bound protein or cytoplasmic or even nuclear. So once the primary antibody has been bound and the excess has been washed away, then we apply the secondary antibody, which is designed to go and bind to the primary antibody. And these secondary antibodies will have on their other ends these chromogens. Chromo refers to color, so these are color-generating structures. So when a chemical is applied, it reacts with the chromogen and turns anywhere in the cell that's bound by this antibody complex a brown color. So we are able to see specific regions or cells in a tissue that's expressing the protein of our interest. Then we have immunofluorescence. And as immuno suggests, just like the immunohistochemistry, you're using the interactions between the antigen and antibody. So we're still using the primary antibody and then using the secondary antibody. But this time, instead of the chromogen, the secondary antibodies have these fluorescent tags. These are the structures when they're excited by either UV or laser light. They emit a specific frequency and wavelength of color that can be detected by a microscope. What's unique about the immunofluorescence is the fact that we can actually visualize more than one protein of our interest in a single tissue slide by applying 1 or 2 or more primary antibodies and then using secondary antibodies to go and bind those specific primary antibodies and having those secondary antibodies tagged with different fluorescent color. So once again, in a single tissue slide, we're able to identify structures that are tagged with green fluorescence. These are microtubules, and things that are tagged with blue fluorescence going in and binding the nuclear proteins, which is pretty cool. Now, onto microscopy, the art of using microscopes. Microscopes are the tools that allow us to look at the tissues under various levels of magnification, all the way up to the level of cellular detail in many cases. The most common type of microscope is the light microscope. These typically have an eyepiece, objective lenses, the stage where the glass slides can be mounted upon, the focal adjustment, and a light source down here. And of course, the source of illumination for light microscopy would be the natural light. It is used to observe the tissues that are stained with histochemistry as well as the immunohistochemistry. Phase contrast microscopy is another form of light microscope in that it uses the natural light as the source of illumination, but it actually has mechanisms that leverages the different refractory properties of the cellular structures, the membranes, the organelles. They will bend the light just slightly differently, which means the cells or tissues actually need not be stained to be observed, which allows for the observation of live cells and tissues with phase contrast microscopy. Next, we have fluorescence microscopy. Now, fluorescence microscopes actually look and function very similar to the light microscopes. In fact, they have natural light source and can be used as light microscopy, but in addition, they have an extra light source in the back, either UV or laser source, that can be used to view the immunofluorescence stained tissues, such as this. Next, we have transmission electron microscopy, or TEM in short. These are actually pretty impressive piece of machinery. They're large, bulky, and very expensive. And instead of using photons, they use the electrons as the source of illumination. And electrons being as small as they are, TEM allows for the greatest amount of magnification and resolution powers to look at the tissues and the cells with the greatest amount of detail. In TEM, electrons actually pass through the tissue, casting different shades of shadows depending on how much electrons were able to pass through the certain parts of the cells. So in TEM, there are areas that are darker. We call these areas the electron-dense areas, such as these. And these can be interpreted as the areas where not enough electrons were able to pass through these regions because there's a lot of materials that are condensed in these areas. So they cast darker shadows, if you will. Then we have the lighter areas, such as these areas and these areas, which we call the electron light areas. And that just means that a lot of electrons were able to pass through these regions because there weren't a lot of things blocking the electrons. Scanning electron microscopy, or SEM, is perhaps just as impressive as the TEM. And they also use the electrons as a source of illumination, but instead of the electrons passing through the tissues, they're actually scattered by the tissues, which is coated with heavy metal in this case. And all these scattered electrons are captured by the sensors, and a three-dimensional surface contour of the tissue is extrapolated, as you can see right here. And lastly, we have virtual microscopy, the frontier of technological advancements, if you will. This is a software or an app that simulates the use of a real microscope on a digital screen. So a user is able to navigate the digital tissue image the same way someone might use the Google map. So here's a demonstration. Here's a virtual tissue slide. You will see me zoom in, move to a different area, zoom in further, then start to pan out. Similar to Google Map. And this is the type of microscopy that you'll be seeing throughout this histology course. Histotechnology and microscopy have huge clinical applications, especially in the field of pathology. Pathology is the study of diseases and the practice of making diagnosis from observing the tissues that have been taken out by biopsies or surgical resections and even peripheral blood smears. Sometimes the pathologists will order some additional studies such as immunohistochemistry or immunofluorescence when a tissue is kind of ambiguous and they need a little more data to confirm a diagnosis. Another way the histotechnology is used in a clinical setting is during surgical procedures. A surgeon can ask a pathologist to come up and make observations of a tissue taken from a surgical margin or from a sentinel lymph node to make sure that those tissues are free of any metastatic cancer cells. So in a procedure called frozen section, a pathologist will take those samples, snap freeze them, section, stain, and make observations all under 20 to 30 minute time frame. So very fast process, which is informative for the surgeons to make the decision as to whether they want to go in and take more surgical margins or do more extensive lymph node dissections or whether they can just close the patient up. The quality of the frozen sectioned tissue is not quite as good as the routinely processed paraffin sectioned tissues, but when speed is of essence, frozen section can be quite informative. And this type of procedure is commonly used by surgical oncologists and dermatologists who specialize in Mohs surgery. Now, before we move on with the rest of the histology course, let's take a brief pause and talk about some histology pro tips, especially when looking at the tissues. Tip number 1. Mind the magnification versus the field of view dichotomy. At low magnification, we're able to see a large field of view or the tissue, but the details on that field will be low. On the other hand, at high magnification, the details will be fairly high, but at the cost of smaller field of view. To put that into perspective, consider this low magnification image of the Earth. Now we're seeing a lot of the Earth, but the details on some of these continents on there are low. When we start to zoom in, let's say onto the American continent, now we're seeing a lot of details there of the topography, but we've lost some other continents in the region, so we're dealing with smaller field of view. Zoom in a little further. Again, the field of view has become even smaller, but the details have increased. When we zoom in one more time onto this tiny little dot, now we're looking at something super specific and detailed. But unless you're from Denver or you're a Broncos fan, you may not know that this is the Empower Stadium at Mile High, which is in Denver, Colorado. So a super duper detailed structure may not be quite as informative when studying histology. That is, unless you become an expert and can recognize a lot of characteristic structures of different organs. Regardless, the best practice in observing tissues is to always start with a low magnification image, then incrementally go into higher magnification in order to always have the contextual information in mind. Pro tip number 2. Characteristic landmarks and unique architecture can easily give away the location. We just saw that example with the Empower Stadium at Mile High being recognizable for Broncos fans. Here's another example. Does anyone recognize where this photo came from? The answer is Chicago. Here's the Willis Tower and some other buildings that are fairly recognizable of Chicago. But again, this image will only be recognizable for those who have been there or have seen photos such as this before. So the familiarity is very important in histology. Pro tip number 3. There is such a thing as too much detail if it's coming from too small a field of view, because it can be disorienting. Here's an example. We have no idea where this photo came from. There's just not enough context. So histology requires context and perspective. Speaking of, let's zoom out. And we can see now that this photo came from the bridge of the nose of a fairly well-known actor, Elvis Presley. The next tip, the same types of tissues can appear differently. For example, let's go back to our favorite actor, Elvis. And as you can see, there are some different versions of Elvis here in grayscale, in color, younger version, older version, as well as the versions with different levels of BMI. But we can recognize each one of these images as that of Elvis. Even an impersonator can be identified. We know that this is not real Elvis, but this person is impersonating Elvis. Histology is very similar. Depending on how we section or how we stain the tissue, the same liver may look very differently but there's underlying pattern that we can recognize as coming from the same organ. Likewise, there may be some impersonators in histology. For example, some metastatic tumors that metastasize to different parts of the body can mimic the surrounding tissues, but with well-trained eyes, we can identify an impersonator like that in histology. The next tip is all about the artifacts. They're natural in histology. Now, artifacts are the things that actually don't belong in living tissues, but they get introduced in one of the many steps in histotechnology or during staining. Some examples of artifacts include tissue tearing, a big space like this in between the tissues that really should be right up against each other. Or sometimes the tissue can shrink, especially during the dehydration process. Or sometimes we can have the tissue that folds upon itself, like these areas, where the tissue is folded upon itself, so it's actually holding onto a little more dye than natural. That's why we're seeing a little more intense staining in these intervals. Sometimes a part of the tissue can actually fade compared to the center of the tissue. That has to do with the exposure to the oxygen at the edge of the glass cover slip. And sometimes we can actually add some foreign particles that don't belong to the tissue, probably a dust particle or even particle from a paper towel or something can get included in one of these tissue slides. Sometimes artifacts are useful in identifying some tissues. Something like this is an adipose connective tissue, and where you see the pale staining area or non-staining area, these are all artifacts where the fat used to be that got dissolved away, and now we're able to recognize these really regular kind of circular structures as the adipocytes. So these are critical component of adipose connective tissue identification. That's artifacts. Next tip is about the representation. We have to remember that initially we started with about 6 inches or so of small intestinal segment, of which we took a small section to embed. And once we have the paraffin block, then we made about 7 micron thick tissue section to arrive at a histology slide like this. And we have to ask ourselves whether this 1 micron thick slice of a 6-inch segment of small intestine is actually representative of that surgical resection. And the answer is no, it's just too small. So we have to be mindful when we get a big tissue specimen to regularly sample and provide enough tissue slides to get a good representation of that surgical resection. The next tip has something to do with the dimensionality. Typically, tissue images are the 2-dimensional representations of 3-dimensional structures. So we need to be mindful of the level of cross sections. For example, when we have a cell that is cut at this level versus this level, the cross-sectional images we get might be drastically different. With the upper cross-section, we might see a cell membrane with the nucleus and maybe some rough ER. But with this cross-section, we'll probably see a circle with maybe a mitochondria and maybe a smooth ER. But that does not mean that this one doesn't have a nucleus. So we need to be mindful of the representation of that single cross-section through a 3-dimensional structure. Another dimensionality conundrum has to do with the plane of section. Let's say we have this bunch of rope and we've made these cross-sections. With a cross-section through this plane, imagine what type of cross-section we might see. We might see a really long longitudinal section through this rope. We might see a cross-section through this rope. and then maybe the longitudinal section of the rope that continues down, and then maybe 2 more here of cross section, and then more longitudinal section like that. However, this cross section or plane of section, we might be seeing some oblique section, and then 2 circles, maybe circle in the back somewhere, upper circle, more circles. I hope you're getting the picture. So depending on when we have a really complex 3-dimensional structure and made a single plane of section, the cross-sectional images that we may be seeing might be super complex, which requires us to really play what I call the mental gymnastics to extrapolate the 3-dimensional shape from the 2-dimensional images. With all these great histology pro tips, you will soon become a histology pro who is able to recognize more and more characteristic architectures from higher magnification but small field of view images. So you'll soon be able to do the histological equivalent of recognizing the Empower Stadium at Mile High or a tower in South Korea. You will also be able to use the situational or surrounding clues to interpret the tissue with greater acuity. For example, here is the Statue of Liberty, recognizable structure, but are we in New York or in Las Vegas? Because there's one in Las Vegas too. And the answer is New York. And I hope you arrived at the answer too, because if we were in Vegas, we'll probably see maybe a roller coaster or a lot of glitzy lights and things like that, which is lacking in this photo. So you will soon be able to do that with histology as well. And you will acquire discerning eye for different versions of the same tissue or even an impersonator or 2 as well. And you'll be able to do that with tissue slides. Caveat, to be a pro, one must visit as many sites or tissues and as many times as possible to acquire that familiarity. And in order to do so, we need to look at as many of these tissues from different angles and different lights as possible.
Thank you for watching this video from the Da Vinci Academy Histology video course, which is completely available on YouTube. To access the corresponding practice questions and histology lab videos, go to our website using the link in the description below.